Okay, so hi everyone. Thank you for attending my presentation. Today I'm going to present our research on automatic library fuzzing through API relation evolvement. I am Jai Ling, and this is a joint work with my colleagues in the University of Hong Kong and the Hong Kong Polytechnic University. So library fuzzing is a software testing technique for revealing vulnerabilities inside software libraries, which typically expose many interdependent APIs. Therefore, to test them, it requires manually crafted drivers to properly invoke the APIs. For example, in the widely used library fuzzing engine like libfuzzer, it generates random bytes for the fuzzing driver, which must properly constrain and feed the inputs into different API arguments. And notably, the API calling sequences orders are also mutable like API arguments, which can reveal more interesting bugs. Due to the limitation of requiring manual labor, there are quite some automatic methods for library fuzzing. However, during our research, we found that they generally face a trade-off between input diversity and API usage accuracy. For some work like Hopper or API Craft, that excels at exploring wider input space, such as wider argument value ranges or mutable API sequences. However, it's at the cost of generating erroneous API usage, leading to false crashes due to API misuse instead of real API vulnerabilities. For example, mutating any API arguments, like the third argument in this glibc API, it will lead to a memory overflow crash, but it's not a real bug. On the contrary, some work like Utopia and Rubik, they focus on API usage accuracy. However, it's generally with limited API coverage and sequence flexibility. So our work is to try to explore the possibility of balancing and improving both diversity and accuracy. We propose our method, our fuzzing tool Nexer, to overcome the above challenge as mentioned, including covering wider input spaces like API numbers or sequence orders, and meanwhile learning more accurate API usage, and then also filtering API misuse to save manual post-processing or triage effort. So accordingly, our three key new designs is that first we propose a modular and scalable fuzzing driver architecture, and then Nexer can perform both static analysis and dynamic learning for API usage. And finally, we carefully design a rule-based automatic filtering strategies to handle API misuse. The overview of our method includes 4 steps. First, Nexer performs static analysis on API consumers, or in another name, library unit tests, and also library source code to generate API descriptions and synthesize code to compose the fuzzing driver. And secondly, the fuzzer can directly generate concrete API call sequences, which are later being interpreted and executed by the driver. And in the last step, the driver would collect execution feedback for the fuzzing engine to categorize crashes and also learn API relations to adjust its generation strategies during the fuzzing. So next, I will introduce the first key design of Nexer's modular driver architecture. So as a comparison, we describe the traditional driver architecture as monolithic drivers. So to compare them, we conclude the 4 major tasks that a good fuzzing driver should complete in the middle here, including like assigning random values to different types of arguments, and randomizing and constraining the call sequence orders, and meanwhile ensuring the inter-API dependencies, and finally signifying the invocation order and invoke the APIs. So in monolithic drivers, these tasks are all intermingled and interleaved inside the synthesized static driver code, which expose many disadvantages, such as being very target-specific and thus hard to scale or automatize. And more importantly, we found that such synthesized drivers are usually error-prone once the scale is up, and usually require manual fixes. For example, if there is any single API misuse generated in the middle of such driver code, the whole driver would become nearly unusable until manual fixes, because otherwise the fuzzing process would keep crashing at the same location due to that misuse. So to modularize these tasks, in Nexer, firstly, our fuzzing engine is API aware. Facilitated by the automatically generated descriptions, our fuzzing engine can directly generate API calls with concrete argument values and sequence orders instead of raw bytes like libfuzzer. And then Nexer has a general interpreter to interpret and execute to interpret the generated seed and perform some low-level but general jobs like setting memory layouts and transferring dependencies between APIs. And then finally invoke the API through synthesized code inside the driver. By distributing different tasks into different components, Nexer has several advantages. First, our API-aware engine makes the adoption of different libraries more easier to automatize, and also makes it possible to dynamically adjust API usage during the fuzzing without the need to modify the low-level driver code. And moreover, the interpreter in the middle is target agnostic, which means that this part of the code doesn't need code generation every time for different libraries. And therefore, the synthesized driver code should only needs to contain the API call entries with correct function signatures, and thus making it easy to synthesize and more scalable. Next, I will introduce the key design of API usage learning in Nexer. Firstly, Nexer performs static consumer analysis by backward data flow slicing to collect API attributes, including like argument constants or data flow dependencies. This is a common design that one can find from existing related works. So a more novel technique in Nexer is that it has a dynamic learning stage. Nexer can tentatively mutate or minimize API arguments and sequence orders, and meanwhile observing the execution behavior to refine its understanding of API relations. For example, in such call sequence seed, the execution crashes at API 5, and then the fuzzer can start to minimize this call sequence by deleting previous calls one by one and execute the seed again. And assuming that after deleting API 4, the execution of API 5 turns to correct, and this indicates a kind of API relations that we call an invalid edge, which are recorded and maintained inside a graph structure inside the fuzzing engine. And reversely, if API 5 executes normally first, and then after deleting API 4, it turns to crash. This is a valid edge inside our API graph. So, for example, these are some real-world relations that we can learn, that Nexer can learn during our evaluation. For example, in the OpenSSL, the big number 3 API naturally cannot precede other big number API like add or subtract. And for valid edges, like the decrypt initialize API must precede the decrypt update API. After learning these relations, Nexer then utilizes some heuristic filtering rules to categorize them and then correspondingly update the call sequence generation strategies. For example, through the collective feedback, including call stack frames or error types from address sanitizer, or the concrete memory violation addresses, plus some design rules like, for example, checking an invalid edge source node if it contains a free call. It can categorize the first two API relations with its corresponding crashing seed as a UF misuse. And then after applying a series of filtering rules, the remaining unrecognized crashing seed and relations are marked as suspicious vulnerabilities for manual triage later. Due to the time limit, it's hard for me to cover all the technical details. So if you are interested, please refer to our paper about more details like how we learn argument constraints by inserting red zones and examining the memory violation addresses, and also other concrete filtering rules. So for evaluation, we summarized two research questions. First is how effective is it especially when comparing with existing works? And second is how effective is its different components contribute to its performance. For the first question, We tested Nexer on 18 libraries, and it found 27 new vulnerabilities within 24 hours with 5 CV assigned currently. And when comparing with existing works like manual drivers in OSS bus and automatic methods like Fuzzing, Utopia, and Hopper, Nexer can achieve 48% more code coverage with 19 additional previously unknown vulnerabilities. And also, Nexer can filter 93% of API misuse, while another similar work can only filter 47%, which puts a heavy burden on manual post-processing. For the second question, we conducted an ablation study that by disabling and enabling the static consumer analysis. And we found that the API usage learned statically can improve the code coverage by 10% with 8 more bugs. And similarly, we found that the dynamic learning stage can improve the coverage by 25% with 9 additional bugs. As shown in these example figures, we can see that the decreasing trends of API misuse ratio when enabling API relation learning indicates that Nexer can learn correct API relations to gradually generate more and more effective API call sequences. So for discussion, we have some interesting findings. First is that many bugs we found come from uncovered APIs. For example, OpenSSL has thousands of APIs, while its current manual drivers only cover hundreds. This still shows the importance of effective library fuzzing automation. And secondly, we found that some interesting bugs come from API sequence mutation. For example, there is a hidden bug in the second big number API here, while the existing manual drivers or any existing unit test cannot trigger it by the fixed sequence. However, Nexer can explore more diverse input space by replacing the sequence by replacing the first API to another big number set bit API to conveniently trigger a hidden bug in the later API. So to discuss some limitations, currently Nexer cannot model some more complex API usage like multi-dimensional arrays and its length buffers. And also, we currently have limited C++ support of the synthesized driver. So that's all for my presentation. Thank you. I'm happy to take questions.
Do you have questions from the audiences? Yeah, maybe I can get started. So I mean, a very interesting talk, and maybe this is just a random the comment. And have you guys thought about using the LLM instead of doing the back slicing? I mean, what's your thoughts?
Yeah, that's also one of our future work, but there are some similar works that apply LLM, but I think they also suffer from the monolithic driver architectures issue because it generates monolithic drivers in our terms. So they have the scalability issue here. But we also found that one of our future work could be using LLM to help humans do the last jobs that are the manual post-processing of API misuse. So that could be a potential future direction.
Thank you very much. So we have, yes.
Thanks for the talk. I had a question about the heuristics you use to filter out false positive crashes.
False positive?
Yeah, right. You talk about some heuristics to filter out wrong crashes to learn better API sequences.
Yes.
Right. Don't you find that sometimes these heuristics are hiding real bugs? So you are actually filter out something that you actually is useful, because having a lot of bugs doesn't mean that they are bad bugs by design.
Yes. So we carefully design a series of filtering rules, and then we perform during our whole evaluation we perform manual validation on all the filter misuse to try to find if it mistakenly filtered true bugs, and found that there are no true bugs being filtered because the filter API misuse are apparent and obvious, but is the major, but has a lot of takes a lot of parts. Okay. So but we have false positives that are mistakenly that cannot recognize API misuse due to some, like, for example, more complex API usage that it cannot model. So that part is the part that currently require manual triage, and also maybe make large language model to help human here.
All right.
Yeah.
Okay. Thank you.
Okay, thank you.
Is there Palmerion again? Great talk. Is there a GitHub for?
Yes, it's in the paper. And,
Oh, it's in the
I
paper. Okay.
forget. Yeah. I forget. Sorry about that. Okay. Thank you.
Yeah. Do you have more questions? No? Yeah. Let's thank our speaker again. Thank you.